Okay, this is an introduction to probability worked example. So here we are dealing with sampling without replacement. Okay, so it's a straightforward enough example. It should only take us a minute or two. Okay, so we have a lot of 100 semiconductor chips that contain 20 defective components, 20 defective chips. Okay, two chips are selected at random without replacement from the lot. The assumption of independent events is valid here. Okay, so here's 4 exercises. What is the probability that the first one is defective? What is the probability that the second one is defective given that the first one was defective? What is the probability that the second one is defective given that the first one was not defective? And what is the probability that both chips are defective? Okay, so let's go through them one by one. But first off, let's just restate the information we were given. A lot contains 100 semiconductor chips, of which 20 are defective and 2 are selected without replacement. So essentially that's important there. So when you take one out, there's 99 left. Okay, when you go in to take the second one. And if you take a second one out, that means there's 98 after that, and so on. Okay, that is the importance and the relevance of without replacement, which is very important. So probability that the first one is defective, well, this should be straightforward enough. The probability that the first chip selected is defective can be calculated as follows. The probability of first is defective is that we have 100 chips to start off with, 20 of them are defective, so if we take one out at random, there is a 20% chance that it is defective, 0.2. Okay, little glitch there, don't worry about that. Exercise B, the probability that the second one is defective, given that the first one is defective. Now this is where you have to sort of be a bit more careful, okay? So we have, just from the previous scenario, there was 100 chips, and 20 of them are defective, and we pulled one out. That means there are now 99 chips left in the batch, okay? And because we've taken one out already, that means that there's only 19 left. Okay, so you just have to think this through in your head. Okay, so if the first chip is defective, we are left with 19 defective chips out of a total of 99 chips. So probability of second is defective, given that that's what that bar in the middle means. That's how we verbalize it. The first one is defective. Straightforward enough. There are 99 chips left. Okay, and of that 99, 19 are defective. So 19 divided by 99. Now, the probability that the second one is defective, given that the first one is not defective. Okay, so this is the opposite case to exercise B. We've taken a chip out and it's fine. It's not defective. That means there are 99 chips left and 20 of them are defective. So all of the original 20 defective chips are still there. Okay, so in this case, we have the probability of the second is defective, given that the first one is not defective. That is 20 divided by 99. Okay. And finally, probability that both chips are defective. Okay. So this is where we consider joint probability and independent events. This is where things start to progress a little bit more. This is where we start to use all of these rules of probability. Okay, so to find this, we need to consider the joint probability of both events happening. So this is the product of the first chip being defective and the second chip being defective, given that the first one is defective. Okay, so that is equal to the probability that the first is defective, which is 20 divided by 100, times the second is defective, given that the first one is defective also. That is 19 divided by 99. Okay, so essentially what we have here is a little bit of calculated work. 0.2 times 19 divided by 99. That is approximately 3.8%, 0.0384. Okay, now we're looking at formulas here, but I think in this instance it is fine just to actually try and rationalize this in your head. Just sort of talk through the narrative behind it. Okay, that's at this where this is probably landing in your course. This is probably early in your introduction to probability course. So, but you will start to notice that I've included some of this notation here, given that probability of second is defective given that the first is defective. So what I'm building there is just sort of setting up something that you're going to see later on. And so what is worth your while is just actually, you don't really need it to answer this question. I think it's fine just to actually sort of just rationalize it in your head. But I think actually what is a good exercise here is actually just to sort of get used to this notation here and just using the mathematical formulation of this problem and making a statement of these probabilities. Okay, because the sooner you get used to this, the better. Okay, so we'll leave it there. It is 0.0384. Do I have anything left to say? No, that's just a summary of the four answers. The first one is defective, 0.2, 20%. Second was defective, given that the first one was not was defective, 19 divided by 20, and calculate the probability that the second one is defective, given that the first one was not defective, 20 divided by 99, and finally both are defective, 0.0384.